In this video, we'll walk through example 3.6 from page 47 of the Seaborg text. The premise of this example is that we have a stirred tank that's used as a CSTR, and we want to know whether the stirred tank is well mixed or whether it's poorly mixed. If it's poorly mixed, there may be things like recirculation zones or dead zones or other non-idealities in the mixing. So what we'll do is we'll model how the concentration of a tracer leaving the tank should change with time if the tank is well mixed for two different inputs of the tracer. Then we could perform an experiment where we add the tracer to the tank and we monitor the concentration of the tracer leaving the tank to see if it behaves according to the model, in which case we can assume that the tank is well mixed. If the tracer concentration leaving the tank doesn't look like what the model predicts, then the assumption of perfect mixing is probably invalid. We're going to do this for two different inputs. One is an impulse test, in which the input concentration of the tracer is an impulse, and the other will be a rectangular pulse input because the impulse is not really physically realizable. We'll use a rectangular pulse input to approximate the impulse input. Part A of the example asks us to find the magnitude of an impulse that would model the total amount of material added with a particular rectangular pulse input that looks like this. The concentration of the tracer entering the tank at the steady state is 1, and then at time 0, the concentration of the tracer is suddenly increased to 6 for 0.25 minutes or 15 seconds. And then after 15 seconds, the concentration of the tracer is dropped back down to the steady state value. Then in part B of the example, we'll find what the impulse and pulse responses of the reactant concentration leaving the reactor, that is C, should be for both the pulse and the impulse inputs. First, we'll find the magnitude of an impulse that would model the total amount of material added with the pulse shown at the right. This pulse begins from 1, goes up to 6, and then comes back down to 1. And we want to know the total amount of material added during this rectangular pulse input. That is, what's the area under this curve? So that we can choose the right value for the magnitude of our model impulse. The textbook does this using the variables Ci for the inlet concentration and C for the concentration leaving the tank. But we're going to do this defining new variables which we'll call perturbation variables. Our perturbation variables will be chi, which is Ci minus its steady state value, and chi, which is C minus its steady state value. Chi for the rectangular pulse input then is 6 minus 1 when t is between 0 and 0.25, and it's 0 everywhere else for t less than 0 and for t greater than 0.25. We can find the area for this pulse by integrating this, and we find that it is 1.25 kilogram mole minutes per meter cubed. Therefore, the magnitude of our model impulse input should be 1.25. Next, we'll find the impulse and pulse responses of the reactant concentration leaving the reactor. And we'll do this in terms of the perturbation variable chi instead of the variable C. To do this, we'll write a species mole balance on the tracer. The accumulation of the tracer is equal to the rate at which it enters minus the rate at which it leaves. Therefore, we can see at steady state, Ci must be equal to C in order for the accumulation to be equal to 0. We can write the steady state version of our component balance for the tracer, and then we can convert our balance equation to the perturbation variable form by subtracting the steady state version from the dynamic version. Subtracting these two equations introduces C minus C bar in the derivative, Ci minus Ci bar, and C minus C bar on the right-hand side. Those can be identified as our perturbation variables. So the balance written in terms of perturbation variables is d chi dt equals q over v chi I minus chi, where q over v is the reciprocal of the residence time for the tank, tau. We also need an initial condition to solve this. The initial condition of the perturbation is that chi is equal to 0. Now we replace the inlet concentration perturbation with either chi for our pulse input or chi for our impulse input to determine how chi should change with time. We'll do the impulse first. The impulse input is A times the Dirac delta function, where A was the area under our rectangular pulse input, or 1.25. Taking the Laplace transform of this dynamic equation and then solving for capital Chi of S, we have an algebraic expression that we can invert back to the time domain. And we find out that the perturbation in the tracer concentration leaving the tank should vary as A over tau e to the minus t over tau. Now for the rectangular pulse input, which is the physically realizable one, we do the same thing, replacing the input perturbation with our rectangular pulse input, which has the Laplace transform shown here. Again, we can solve the algebraic equation for capital Chi of S and invert this back to the time domain. Note here that we have an exponential in S in the Laplace domain, which means that this term is going to represent a time delay in the time domain. In order to invert this back to the time domain, we need to change all of the t's to t minus 0.25 and then multiply by the step function. The result is the sum of two exponential decays, one of which is delayed in time and multiplied by a step function. Or we can write this as a piecewise function for t less than 0.25 and t greater than or equal to 0.25. Here we've plotted the solutions for the impulse input and the rectangular pulse input. You can see that these two curves match each other reasonably well. This means that the rectangular pulse input is a pretty good approximation for our impulse input. And if we were to perturb the tracer concentration using our rectangular pulse, we could see whether that perturbation in the effluent concentration matches these curves. If it does, then we can assume that our tank is well mixed. If it doesn't, then there must be something wrong with the model, and the tank is probably not well mixed. In the next video, we'll show how we can use MATLAB to perform Laplace and inverse Laplace transforms.